So here we're going to take a look at the hydroboration reaction, and specifically we're talking about the hydroboration for alkenes. So the hydroboration reaction, a lot of the credit for its discovery goes to H.C. Brown back in the 1950s. And Brown is the chemist who's by far most well known for his work in this reaction, as he spent the better part of the next 50 to 60 years doing research in this area, and would eventually go on to win a Nobel Prize in chemistry for his work on hydroborations. The hydroboration is another reaction which adds water to an alkene, just like with the hydration as well as the oxymercuration. If you recall, with both of those reactions, those were hydration type reactions where one of the carbons of the alkene got a hydrogen added and one of them got a hydroxyl group added. Hydroboration gives a similar result. The difference with hydroboration is that it's an anti-Markovnikov process. And by anti-Markovnikov, we mean that the OH group ends up on the less substituted carbon. So the reaction works by the addition of borane, followed by a second step where we typically add hydrogen peroxide and base. And again, the result is now the hydrogen goes on the more substituted carbon and the hydroxyl group on the less substituted carbon. Alright, so how does this reaction work? Well, one of the things that's a little bit different about borane than other reagents that we've used is boron has very low electronegativity. In fact, it has lower electronegativity than hydrogen. So if there's any polarization at all in the BH bond, it's that the hydrogen would have the partial negative and the boron would have the partial positive. And so the atom with higher electron density is going to be attracted to the more substituted carbon. In addition to that, the boron is usually at least loosely coordinated to a solvent molecule such as THF here. And that adds to the size of the boron. And so quite often the boron is going to prefer to be where there's more space. So in order for the boron to add, it's really a one-step mechanism. The alkene attacks the boron and the hydrogen simultaneously attacks hydrogen. But notice here that the boron still has two hydrogens attached to it. So this step can repeat. To give us a dialkyl borane, and it can happen a third time. Until that boron no longer has any hydrogens left. And so what we end up with here is a trialkyl borane. This is the point in the mechanism where we would add the hydrogen peroxide and the base. And so when we add the hydrogen peroxide, it gets deprotonated and it attacks boron. And so we get an intermediate that looks like this. From here, one of the carbon groups shifts over, grabs onto the oxygen, and kicks out hydroxide. Give us this intermediate. And as you may have guessed, since we've got two more R groups, this process can repeat 2 additional times. To give this intermediate, and then this intermediate basically falls apart in the presence of water to give us a boron byproduct plus 3 equivalents of the alcohol. So the key pieces in this reaction is, again, it forms an alcohol, but it forms the anti-Markovnikov, or the less substituted alcohol. Hydroboration can also have an impact on other reagents, so you have to be careful, especially if there are alkynes as well as carboxylic acids present. Both are functional groups that can react under these conditions. And then we can finally just look at a couple of other examples. So here at this example, we start with styrene. And in styrene, there's just the one alkene. And so the alcohol ends up, as we've said, on the less substituted carbon. And that's going to be true for any alkene that we use. So overall, what we have here is a procedure that is complementary to our acid-catalyzed hydration or our oxymercuration. Both of those give us the most substituted alcohol, while hydroboration is a reaction we can use to give us a less substituted alcohol.